Have you been to a carnival and played the Laughing Clowns game? You probably have, as have I. And I can tell you that I absolutely hate clowns, especially the laughing kind, because rather than being naive and making you laugh, they've made me angry once I found out that it's very difficult to win a good prize at the game. So, how is the game played? Well, we have a laughing clown head, as you can see, and as it spins from left to right, you have 5 ping pong balls which you insert into the mouth one at a time, and it comes out at the bottom next to one of 9 columns with numbers on them, and the sum of the 5 numbers will give you a prize. And that's where the challenge is, because it's very difficult from the sum to get a decent prize, as we will see. Here is our clown, and the numbers we have at the bottom are 2, 4, 5, 1, 3, 6, 4, 2, 3. But in the end we will see that the order of the numbers doesn't really matter, it's the actual numbers that make the difference. So we can insert a ping pong ball one at a time. In this case, the total, as you can see, is 14. Here's another one, total of 15. And total of 17. What do you think the smallest total that is possible is going to be? It is 5, isn't it? What's the maximum total? 30? Yes. Now that we've seen the simulation of the game, what's the chance of winning a particular prize according to the total? Now remember, we are dropping 5 ping pong balls one at a time and summing the 5 numbers. One way to look at it is that we have 5 boxes to fill with a number taken from one of the 9 numbers. They're the 5 boxes. How many numbers are possible to fit into the first box? In fact, we have a choice of 9 numbers for each box, don't we? Because repetition is allowed. So can we work out the total number of possible combinations out of that? Well, one of the principles of permutations and combinations is called the multiplication principle, which really means that to get the total number of combinations, we multiply the numbers. So there we have it. 9 times 9 times 9 times 9 times 9, or 9 to the power of 5, comes out to be 59,049. So that's how many combinations there are altogether. Is that going to help us? It will. Now, what we can look at is just the total combinations for the first few totals. And as we saw, to get a total of 5, there's really only one way. Each of the ping pong balls must land on the number 1. So there's one way of doing that. To get a total of 6, there are 10 ways, as I will show you. There they are, first 5 ways anyway. In the first row, 1, 1, 1, 1, 2 means that the first 4 ping pong balls land on the number 1 and the 5th one lands on the number 2. And of course, because the order is important, you can see that we can have another 4, which makes a total of 5. But we said the answer is 10. So how does that come about? Well, remember that out of the 9 numbers that the ball can land on, there are 2 2s. So in effect, when you see a 2 in any of the rows, that could be either one of the 2 2s. So in other words, we have twice the number of combinations that are shown there. So the 5 becomes 5 times 2, which is 10. Now we can obtain the answer in a much more structured mathematical way by using some laws of mathematics, particularly permutations and combinations. Have you come across this expression? If you have n objects arranged in a row and there are n1, n2 and so on repetition of some of those numbers, then the number of ways they can be arranged is capital N factorial, that's what the exclamation mark means, divided by n1 factorial, n2 factorial and so on, where n factorial is the product of the numbers in descending order down to 1. So for example, 4 factorial would mean 4 times 3 times 2 times 1, which is 24, and so on. And we can use this in our expression. So for getting a total of 6, well, we know there are 5 numbers we are choosing, or 5 ping pong balls, so capital N is 5, and 4 of the numbers are landing on the number 1, so let's say that the number of repetitions n1 is 4, and For the number 2, it only appears once, so n2 will equal 1. So plugging those into our formula, we have 5 factorial over 4 factorial times 1 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 1, which comes out to be 5. And now, for the same reason as mentioned before, because there are two 2's to choose from, the total actually becomes 5 times 2, which is 10. This mathematical approach is more effective as the total becomes greater. Here we are, total of 7. Total number of ways will be 50. One combination is 11122. So using our formula, n will be 5 again, n1 will be 3 because there are 3 1s, and n2 will be 2 because there are 2 2's. And plugging into our formula, we get 10. But again, because there are 2 2's to choose from, each of those 2's that appears in our row has 2 choices. So in fact, our 10 combinations become 10 times 2 times 2, which is 40. Now another way of getting a total of 7 is 11113, and again applying our formula, n equals 5, n1 equals 4, n2 equals 1, and the number of arrangements combination is 5. And for the same reason as before, 2 3's appear in the 9 numbers we have, so there are 2 choices for that, and that means that the number of combinations is 5 times 2, which is 10. So the total becomes 40 plus 10, which is 50. They're increasing rather dramatically, aren't they? Let's do just one more, just to make sure we understand the method. The number of ways of getting a total of 8 is 170. Here's one way, and applying our formula, 20 ways of doing that. For each 2 and 3 that appears, there are 2 choices for each. So our number of ways becomes 20 times 2 times 2, which is 80. Another way of getting a total of 8, again, applying our formula, we get 10 ways of doing that, but because we have 2 choices for each of the 2's, we have for the total 10 times 2 times 2 times 2, which is 80. And finally, another way of getting a total of 8, as you can see there, and applying our formula, there are 5 ways of doing that, but there are 2 4's, so the total number of ways for that becomes 5 times 2, which is 10. So the grand total will be 80 plus 80 plus 10, which is 170. And of course you can continue doing this method all the way up to a total of 30, and it will take you quite some time to do that. Here's a table that lists all those total numbers. We've done up to a total of 8, and you can see how they rise dramatically and then reduce again, almost in a symmetrical way. We can also look at it a slightly different way. If we work out the percentage probability for the number of combinations, for example, to get a total of 5, there's one way of doing that, and we know there are 59,049 ways altogether, so as a percentage, that will be 1 over 59,049 times 100, which is approximately 0.002, a very small percentage. Down the table, the percentages increase. The maximum is about 11.6% for a total of 16 or 17. And if we plot the graph, as you can see there on the right, and connect it with a smooth curve, it almost looks like a very nice symmetrical curve, which we'll look again in a bit more detail in a moment. Here's a simulation for 10,000 trials of putting 5 ping pong balls into the mouth of the clown. You can see a pattern already emerging. It looks quite symmetrical, doesn't it? We're getting to 3,000 iterations, and you can see on the very left and on the very right, very difficult to get a total of 5 or 30, whereas in the middle section the rectangles or the frequencies are going up quite quickly. So we're getting to 6,500 iterations, and the shape of the graph is very symmetrical as expected. Here we go. 9,000. And lastly, 10,000 trials. And if we connect them with a curve, do you recognize that curve? From probability theory, it's the normal distribution curve, which is a good sign that the variables, in this case the spread of the totals, follows the normal distribution curve, which is not quite true in reality, is it? Because the player does have some control over the input. That means when the ping pong ball is inserted. So what conclusions can we make? I've color-coded the table just into broad areas. So in the middle section in yellow, I've labelled it easy, and by that I mean that because the percentages are relatively high, getting a total of, let's say, from 14 to 19 is probably the easiest thing to do. And you can see there right at the top, getting a total of 5, and also right at the bottom, getting a total of 30. The percentage is about 0.002, and I would think that getting that would be a near impossible feat. Below that, perhaps in the very hard section, getting a percentage of about 0.02 to 0.08, or a total of 6 to 7. Other end, perhaps a total of 27, 28 or 29. Let's suppose that we allocate $1,000 for a total of 5 or 30. Then the very hard equivalent would be approximately $250, because getting a total of 6 or 7 or 27, 28 and 29 is approximately 4 times easier than the near impossible. So that means that we divide by 4, which gives us $250. And if you follow that method, a hard would be equivalent to about a reward of about $5 and easy about $2. So what does all this mean in terms of the game itself? You might have noticed that the prizes shown next to the numbers fit this pattern. So for example, the number 5 or 30 would be probably for a prize that is significant, perhaps something like quality teddy bear or a watch, something like that. And getting an easy total from 14 up to 19 would be a relatively minor prize, perhaps a little toy of some sort. So really, the creators of the game must have been very clever mathematicians to have figured it out in this way. So the bottom line is clowns rule. Until next time, bye-bye.